Today we shall be taking up a very important topic, polyphase decomposition. Now, those who have the electrical engineering background, they know in electrical engineering polyphase means, or say 3 phase systems we have in the power circuit. Polyphase means each of the phases will be having lead or lag over the other, lead or lag of angle. So, here it is a little different, but we will see the principle is more or less identical. It is the response of a particular channel which will be having a different phase from the other channels, all right. So, there is a kind of a phase shift that we give in the response. We will see how it is done. FIR filters you have studied in the DSP course. FIR filters, when you synthesize, you can have a direct form, okay. You can have a cascaded form, what is the advantage of cascaded form? Why do you cascade filters? All right. Direct form, it is like this: H0 plus H1 Z inverse plus H2 Z to the power minus 2 and so on, say Hn minus 1 Z to the power minus n minus 1. Suppose this is an n point sequence FIR filter. So, you take multipliers, this is xn, okay. Then you multiply by H0, take derivatives, multiply by, take the difference operators Z inverse, then multiplied by H2 and so on, and then add them together. This is the direct form. And so on, all right. If I factorize it in the form of H1Z into H2Z and so on, then I can have, say, quadratic factors. Then I will have just structures like this coming again in this form. This is Z inverse, this is again Z inverse, added together and so on. So, such blocks will be coming as H1, H2, H3. The advantage is whenever there are some drifts in the parameter values, only the roots associated with this block, with this quadratic, only will be affected. Whereas here, if there is a shift in the value of H2, it will be affecting all the n minus 1 roots, all the zeros will be shifting, okay. Whereas here there is zeros corresponding to this particular block, this quadratic will be affected, it will not be affecting others. So, you are going to restrict the movement of zeros due to the drifts in the parameter values. Parameter values change because of truncation, you have a finite register length, you have an 8-bit or 16-bit register. So, all these coefficients will be truncated, either you round off or you truncate. So, there will be some error, all right. So, these errors will have some effect on the location of zeros. So, anyway, this is the direct form and the cascaded form. There is also another form, you must have studied it, that is the lattice structure. We are not going to discuss about the lattice structure right now. And there is a fourth form, that is the one that we are going to discuss today, the polyphase structure or polyphase form. It is like this: Hz I can write as H0 plus H1 Z inverse. Say I have up to H10 Z to the power minus 10. Okay, I can pick up the alternate terms, that means even terms and odd terms. I call it H0z H1z one may write like this. H9 z to the power minus 8. Okay. Now, this is a function of z to the power minus 2. So, H0z, I can write this as some E0 z squared. It is a function of z squared, where E0 z will be H0 plus H2 z inverse plus finally H10 z to the power minus 5. Okay. Similarly, H1 z can be written as E1 z square, all right, where E1 z is H1 plus H3 z inverse and so on, H9 z to the power minus 4. Do you agree? It is a polynomial in z to the power minus 1, both of them, E0 and E1. So, that polynomial sorry, z, if you replace by z squared, we will get H0 and H1 z. Okay. Sorry, if I take out z inverse, this is H1, all right, this is E1, E1 z squared. So, E1 z means this. Okay. So, Hz can be written as H0 z, okay, I will write E0 z squared plus z inverse E1 z square. If we have, instead of picking up alternate terms, every third term we pick up, then Hz can be written as E0, what should I write? Z cubed, do you agree, plus Z inverse plus okay. So, generalizing this, if I have m such groups, Hz can be written as E0 z to the power m plus z inverse E1 z to the power m. Last term will be m minus 1 minus, okay. See, for every third term, if we pick up, that is, if it is having 3 polynomials, then z to the power minus 2, and that is, the index here is 3. So, here it will be 2, it will be ending at E m minus 1 z m, and z to the power the same number m minus 1. So, we can write the polynomial, any polynomial, we can have any number of such groups. So, suppose L is the, okay, number of polynomial groups. What will be the terms of this, any general term, say Ek or Em Z, what will be this polynomial? H if you have an infinitely long sequence, all right, let us consider a non-causal system, that is n extends also up to minus infinity, then and we choose the terms like this, say every lth term, then it will be ln plus m, is it not? If you have taken say the every third term, so this will be 0 plus 1, 2 into 0 plus 2 into 1 plus 1, like that. If you have taken three terms, then the coefficients of this or any of these, any emth term will be appearing like this. Okay, you can group them in this manner. Okay. So, the realization for this first one is E0 as it is, E0, suppose we take this one every third term. So, E0 z cubed, all right. Next there is a delay element E1 z cube, next E2 z cubed. Okay. This is Yn. You can try a few more structures, it is very simple, all right. You can have fourth order or higher order realization. For a 3 branch, this is a 3 branch polynomial. Polynomial realization. So, we have got E0 as H0 plus H3 z to the power minus 3 plus H6 z to the power minus 6. Okay. E1 was H1 plus H4 z to the power minus 3 plus H7 z to the power minus 6, whole thing into z to the power minus 1. Okay. I mean E1 gets multiplied by z to the power minus 1, that is what I meant. Okay. And E2 similarly will be H2 plus H5 z to the power minus 3 plus H8 z to the power minus 7, sorry, H8, okay, and then z to the power minus 6, sorry, minus 6 z to the power minus 2. So, all of them are having the same order. Of course, if you have 9 points, then only it will be 3 each. If you have 10 points, then this will have 4 element set, others will be 3. So, the highest will be the 4 element set. Now, if we realize it, if we try to realize this filter, it will be like this x n suppose we have a multiplier h 0, then I can put z to the power minus 3 then h 1 h 2. Okay. I can put another z to the power minus 3. Okay. Then from here I can have a multiplier h 6. Now, you see h 6 is multiplied by z to the power minus 6 added with h 0 and h 3 z to the power minus 3. So, z to the power minus 3 is here. So, I will take a multiplier here h 3 and add them here. Okay. This is the output corresponding to the first phase. H 1 similarly will have H 3, I can take from here H 4 and H 5. Okay. H 4 is added with H 4 z to the power minus 3 added with H 7 z to the power minus 6 and added with H 1. After that, the total sum is multiplied by z inverse. So, from here I can take 8. Okay, let me multiply this by H 7, this by H 8. So, H 7, H 4, this is H 7 into z to the power minus 6, H 4 into z to the power minus 3 and H 1, this will give me an output which finally if I multiply by z to the power minus 1, I will get the second output. All right. And lastly, H 2 plus H 5 into z to the power minus 3 okay, and H 8 these three will give me H 2 plus H 5 z to the power minus 3 plus H 8 z to the power minus 6. Whole thing will be multiplied by z to the power minus 2. I could have made use of this before addition. Okay. So, I will put z to the power minus 1 block here, okay, and then add with this. Is that all right? And then this product is finally multiplied by z to the power minus 1. So, these are all getting multiplied by z to the power minus 1. This is getting this set, this sum is getting multiplied by z to the power minus 1 and again z to the power minus 1. So, this is the final output, this plus this y n. Now, if you have a linear phase filter, what is the advantage of linear phase filter? H0, suppose there has to be a symmetry from the two ends, suppose it is symmetric filter, then H0, H8, H1, H7, like that you have symmetry of elements. So, you need not have different values, H0 is same as H8. So, you will have same multiplying elements, and you see the total number of elements will be much reduced. You can try for an antisymmetric filter also. So, try at home the final structure for an antisymmetric filter and a symmetric filter having 3 or maybe 4 levels of decomposition. So, we can have, if it is an FIR linear phase, I will take up a simple example, you can try a little more complex structures. Suppose we have H0 plus H6 z to the power minus 6. I have coupled a 7 element linear filter, I have coupled the terms H1 plus H5 z to the power minus 4 into z to the power minus 1 plus H2 plus H4 z to the power minus 2 into z to the power minus 2 plus H3 z to the power minus 3. I can write like this, and H6 is H0. So, it is basically H0 into 1 plus z to the power minus 6 plus H1 z to the power minus 1 into 1 plus z to the power minus 4 plus H2 1 plus z to the power minus 2 z to the power minus 2 plus H3 z to the power minus 3. Okay. So, this one can be realized in a very interesting way. You have each rectangular block is a DIL element Z inverse, Z inverse, Z inverse. Okay. Again Z inverse, I have just put the DIL elements in chain. Now, you see what I am doing, you take H0, it has to be added with say 1 plus z to the power minus 6. So, there are 6 DIL elements. So, I will take the output here, add them together. I have done this addition. Take this out, multiplied by H naught. Okay. So, can you suggest what should you do next? It is z to the power minus 1 and z to the power minus 4 minus 5. Okay. So, z to the power minus 1 has already been taken, and this is z to the power minus 5. So, add them here, and then this output you take here. What should be the multiplier? H1. Okay. In signal flow, we use just the arrow for the multiplying constant. Okay. So, I need not always write a constant with any block. Similarly, this one I add with this output. Okay. This is to be multiplied by H2, all right. Then it is better to show the direction by an arrow like this and the constant by a little bigger arrow, all right. In analog gains you show multiplier like this, so it is like this. In many books they use a small arrow both for direction, Z inverse or any multiplier, okay. That is all allowed. So, Hz, okay, any signal xz I can write therefore in the decomposed form as sigma z to the power minus k xk z to the power m, k equal to 0 to m minus 1, is it not? If there are m such subgroups, then k will have maximum m minus 1. The polyphase components, these are the polyphase components, xkz will be say xkn z to the power minus n, n tending to infinity. Okay. And what is this in terms of the original sequence xn? From the original sequence you are picking out say either every third term or every fourth term or every mth term. So, it will be x mn plus k z to the power minus n. Is that all right? Mind you, this is a polynomial when I am writing in terms of z to the power minus 1 only, polynomial of z to the power minus 1, and this will be expressed in terms of polynomial of z to the power m. So, in a matrix form I can write this as 1 z to the power minus 1, z to the power minus 2, z to the power minus m minus 1 into x naught z to the power m, x 1 z to the power m, similarly the last one x m minus 1 z to the power m. All right, this summation I have written in this form. Is this all right? So, for the m band polyphase decomposition will look like this. I give a signal xn, I have a downsampler m. Downsampler does what? You are picking up only the mth terms in the given sequence. So, we are downsampling by m. This will give me the terms x mn, all right, every mth term. Again downsample by m. This will give me x mn plus 1 mind you this is plus 1, we are generating the next set, that is why this is Z, not Z inverse. Again downsample by m x mn plus 2 and so on. Lastly, it will be x mn plus m minus 1. N is any number varying from minus infinity to plus infinity, integers. Is this structure all right? It is like any of our previous forms. Okay. So, like this. This series is H1, H4, H7, all right. This series is H2, H5, H8. So, the general term is 2 plus 3 into n, 1 plus 3 into n. So, the starting value is 1, 2, 3 etc., and this is Mn. For an IIR filter, polyphase decomposition is rather difficult. For IIR filter, it is not straightforward. A simple example will give you, say 1 minus 3 Z inverse divided by 1 plus 4 Z to the power minus 1. Suppose this is an IIR filter. How do you decompose into such terms, say in terms of Z square, say if we take polynomials of Z square. So, I reduce this if I multiply by 1 minus 4 Z inverse. Okay, multiply both sides by the same factor. So, the denominator becomes 1 minus 16 Z to the minus 2. So, I have got a polynomial in Z to the minus 2. Okay. This one 1 minus 7 Z inverse plus 12 Z to the minus 2. So, I can write this as 1 plus 12 Z to the minus 2 by 1 minus 16 Z to the minus 2 minus 7 into Z inverse, okay, minus Z inverse into 7 by 1 minus 16 Z to the power minus 2. So, it is like our first E0 Z square plus Z inverse into E1 Z square. This is Z inverse multiplied by this function E1. It was so simple because we have taken a very simple polynomial. Reducing a polynomial to a polynomial of quadratic terms, all right, will not be so simple. Had it been a little more involved, then it will be difficult. So, earlier we saw xn, if I downsample xn and if I have a filter here hz giving me an output yn, this is equivalent to xn hz to the power m okay. That means if I have a downsampler followed by a filter Hz, I can interchange their positions, but then the filter has to be changed, Z has to be modified to Z to the power m, okay, then you will get identical output. This we had discussed earlier. Now, when you are going for a decimator, you require a low pass filter. This we saw earlier. Why do you need a low pass filter? That is an anti-aliasing filter. Okay. For downsampling, you require a low pass filter. Let this be some Hz. Okay. Mind you, this Hz has got nothing to do with this. This was only an equivalence relation. Okay. Now we are talking about a decimator. Whenever we want to decimate the sequence by a factor m, we must check whether aliasing takes place or not. So, we have a band limited filter. So, this is a low pass filter Hz. Okay. This Hz, suppose we write in a polyphase structure of Z to the power m, then what do we get? And then we will be using this relation. Okay. To be more specific, okay, to avoid confusion, let this be written as H dashed Z to avoid any confusion with this Hz. Okay. So, this is a relation that we have established earlier. Now, we are going to make use of it at a later stage. Suppose you have to design this Hz. Now, we decompose it in a polyphase form. Okay. So, if we decompose Hz, it will look like this. Just now we have seen the decomposition, the earlier one. Anyway, we will have it here. E1 Z to the power m, E0 Z to the power m, again a delay element, E2 Z to the power m, and so on, is it not? E m minus 1 Z to the power m. Okay. And this is Hz, all right. This entire block is Hz, and then we put the downsampler. Now, each one of them can be treated separately, is it not? And if I put a downsampler, that means I can put the downsamplers here. Okay. And then I can interchange by this relation, all right. So, if a downsampler is having previous to this H Z to the power m, then I can put H Z only. So, this will be equal to, okay, I will take this page. This will be equal to, what was the frequency here, Ft, and this is also Ft. Okay. The frequency here is Ft by m. Okay. And now we are having Ft I can put the downsampler first, then this will be, what will be this one? E0Z. That is minus 1. E1Z and so on, and keep on adding them. I will get the same output yn. What about the frequencies? Now it is here ft by m, and here also ft by m. Downsampler has changed the frequency, so will be at these points also. This is computationally more efficient. Why? Can you justify? This is computationally more efficient. See, if you have a single Hz, suppose there are 10 coefficients, all right, or say 9 coefficients, and there will be 9 multiplications and then 8 additions, all right. It will take time, unless the entire cycle of, for each stage I have to have the input sequence computing all these multiplications and additions will be taking place here, and from here we will be picking up only a few of them, all of them are not required, but when the chain comes, all the computations will continue, is it not? And from here you are selecting only the mth terms. When you are picking up mth term, so first term you have picked up, you are waiting, the computations are going on, you are not interested in it. So there is a lot of idle time for many of the elements, and unless the entire cycle of computation is over, the next set of data cannot be taken. Now what happens here? You are downsampling the data right in the beginning, you are choosing the data, you are making a shorter length, and the computations are going on simultaneously in parallel channels. So all the arithmetic operations are going on, nobody is sitting idle. So all these elements will keep on computing, okay, and they are having selected coefficients. Now out of 9 coefficients, here only 3 computations will, 3 terms are there, so 3 multiplications and 2 additions. Only a few additional addition terms will be coming here, but in each of these blocks the number of computations will be drastically reduced, and all of them will be done in a parallel mode, okay. So this is computationally more effective, very efficient. So we have got xn, hzm, m, and yn. This structure we have reduced to this form. So if there are say n points and nk points per parallel branch, all right. So the number of computations per branch will be nk multiplications and nk minus 1 additions, is not. So summation of nk will be equal to n, all right. These are number of additions in each block. Number of multiplications, earlier it was totally n, and here in each section it will be nk, and sigma nk is equal to n, because number of coefficients you are not reducing. If there are 9 points, you are picking up alternately 3, every third one, and you are making 3 groups. So, number of coefficients will be same. Now, let us see an upsampler. If you have E0Z L E1Z L and so on. And you put a Z inverse term here, a multiplier here, okay, and you have L such parallel blocks. Last one will be EL minus 1 L, and this will be the output. Okay. So, you can feed to E0Z, E1Z, etc. If you remember, for a decimator, we had, what was the relation for a decimator? We have seen if it is decimated first, and then if it is Hz to the Hz, if we interchange the position of the decimator and the filter, then the filter will have to be, Z inverse will be replaced by Z to the minus m. Reverse will be the case in case of frequency multiplier. What is it called? Upsampler. So, for an upsampler, it will be E01, E1Z, etc., and then it will be upsampled later. If you put in this fashion, so mind you, this is Z, index of Z. So, this will be put for a downsampler, it will be put on this side, for an upsampler, it has to be put on this side. Now, we will go to digital filter banks. What do you mean by digital filter banks? This is a bank of band pass filters. Okay. We have a common input and we have a large number of filters, say H0, H1, that means H1, H0, Z inverse. Okay. Similarly, all these are there, H1, H2 and so on. Corresponding outputs you get in different bands. That means you have different bands of frequency, all right. You have a band pass filter with varying bands and uniformly distributed in the range 0 to 2 pi. So, for example, we normally talk about low pass filter like this, okay, or a high pass filter like this, or a band pass filter like this, or a band gap or a band pass filter like this, okay, a band gap like this. Now, same is the type of filter. Instead of this kind of a rectangular brick wall characteristics, suppose we have a filter like this. This is one band. Next we take another filter like this. Next we take another filter like this. Obviously, you cannot have all the filters put together, So, the first filter will be filtering frequencies from say 0 to omega 1, next one will be from omega 1 to omega 2. So, it is like this. I have a channel H0 which gives me a filter gain of say a characteristic like this. Then I have H1, this is mind you in terms of omega. So, this is say some omega 1. We will see later on, it need not be symmetric on this side, need not be symmetric on this side. Why? When do you have absence of symmetry? Sorry? When the terms are, the coefficients are complex. For a real coefficient H0, H1, H2, if you have real quantities, then for plus e to the power j plus j omega or e to the power minus j omega, the magnitude will be symmetrical. All right. So, H1, anyway, for the time being I am taking a symmetrical structure. It will be say from like this. So, this is my band. The third one will be like this, and so on. So, how do you design such a filter? So, all of them are basically this gain having a shift of a particular angle. And what is that angle? What is that angular shift? If I have an M bank equal band, all right, equal bandwidth filter, then 2 pi by m e to the power minus j 2 pi by m is the shift. It is shifting delayed by e to the power minus j 2 pi by m. So, whatever is the filter function here, multiply by e to the power minus j 2 pi by m, you will get successive ones. Okay. This is for analysis. Given an input, we are trying to get what will be the outputs. These outputs will be corresponding to different band pass filters. All right. This is what we do sometimes in MFCC. Basically, this is the type of filter bank you use. Okay. And when you synthesize, you take different signals, say V0n, V1n, and so on, and then you have these filters, say F0, F1, F2, F1, F2, F0, these are all similar filters, all right, and add them together. Okay. Finally, you get the output. From various inputs, you get the output. So, when you want to filter out a signal, you have its response in different bands, take these and then moderate them, modify each band whatever you want, okay, and then again add them. Do you get my point? In different bands you are having different responses, so you moderate them. Suppose I want to suppress or I want to modulate certain ranges of frequencies, so that has been done, and then after that you again add them. Okay. So, this is a synthesis filter. We will stop here for today, we will take it up in the next class. How do you get the terms for this kind of output of the filters. Okay. Thank you very much.